Hi, everyone. My name is John Simon. I'm a product and applications manager at Intrepid Control Systems for Automotive Ethernet products. And today I'd like to share with you 10BASE-T1S, 2 years of teaching and 2 years of learning. If you're not familiar with our company, Intrepid Control Systems is a private company in Troy, Michigan. We make network development tools for automotive. So we make hardware to interface with any automotive network, and then we make software to help our customers with different use cases, anything from product development to system integration, debugging, testing, logging, calibration, you name it. All the network development use cases are covered with our software and our hardware. Again, we're located in Troy. We have all of our engineering and manufacturing here in Troy. We also have remote offices in the different regions for supporting, for customer support and sales support. So why are we talking about 10BASE-T1S? We'll talk about background and motivation, why it's becoming relevant. So the evolution of vehicles for the last 30 plus years has been the continuous growth of ECUs with new features, new systems, and the growth of Ethernet within the last 10 years, accompanied by the persistence of legacy networks of CAN, LIN, FlexRay, and some of the even older networks. When you are merging Ethernet architecture with the legacy networks, it requires gateways to bridge the communication between, say, CAN and Ethernet or CAN and FlexRay. And so this is additional complexity, additional software to the vehicle that ideally you'd want to remove if possible. The other thing to consider is that we have gigabit, multi-gigabit Ethernet links available for vehicles, but 80% of the communication between ECUs is a very small amount of that bandwidth, less than 10 megabits per second. So if you look at this diagram here, this is a history of the different legacy networks as a function of time and bit rate. So I've kind of grouped them together in these bubbles. So you can see CAN emerged in the 90s and then has evolved and gotten faster over the years until 2015. You can see in 2005, there was a jump to or a need for higher bandwidth. So this is where the jump to integrate automotive Ethernet started to occur. And you can see its trajectory from 100 megabits up to multi-gigabit. And then at the bottom, you have the low-speed, low-cost networks of LIN and CENT and similar networks. And what you can see here is this gap of needing 10 megabits per second low-cost communication. So this CAN was running out of bandwidth, and it's also inefficient in terms of the size of the payloads. So this was more of a clean sheet opportunity to fill this gap here. So there are two technologies that emerged for low-cost 10 megabit communication. One was an extension of CAN called CAN-XL, and the other 10BASE-T1S, low-speed, low-cost version of automotive Ethernet. So why Ethernet? If you look at the different networks and different protocols, they all deliver certain protocols and certain functions as in that network. So if you look at LIN, it's a very specific purpose, switches and actuators and things like that that are very simple in nature. And what LIN brings you is physical addressing, how to address these devices, some error detection, how to access the media, and then how are messages formatted. So very simple network, very simple protocols. Then if you look at CAN, CAN's more multi-purpose. So it has all the protocols or all the services that LIN does, but then it adds network management and a transport protocol, time synchronization, diagnostics, SecOp, and security. So CAN is more multi-purpose because it has additional protocols to support more complex applications. If you look at Ethernet, Ethernet takes all the services and protocols of CAN and then builds on that to support things like time-sensitive networking. So quality of service mechanisms to ensure that the network is shared among different subsystems and the subsystems don't interfere with each other's function. Different layers of security as well. Different middleware, so some IP, diagnostics over IP, XCP. So you could see Ethernet, I'm calling it infinite purpose because over the last 40 to 50 years, Ethernet's evolved to amend or add new standards to support protocols or adapt protocols to meet new applications. So why is low-cost Ethernet so important? If you're not familiar with vehicle architectures and the evolution of them, there's a movement away from something called a domain architecture. And domain architecture is the evolution of the vehicle as more and more ECUs and subsystems were added. And these ECU or these subsystems or domains are basically segregated. So you have an independent network for HVAC, you have an independent network for powertrain, independent for body. And yeah, there's bridges between these networks, but you can see by this diagram, the colors indicate the different domains, and you can see there's a lot of redundant paths across the vehicle for these different domains. So it was optimal at the time as it evolved, but the technology's made it suboptimal in cost, weight, and manufacturing. So if you look at the zonal architectures, which is replacing the domain architectures, it's a very neat, simple network. You have a central compute unit connected to zonal modules or the gateways, aggregators. They have different names and different customer architectures. They're all connected by a high-speed backbone, gigabit or multi-gigabit. And then you have the zones that consist of medium complexity to low complexity modules. So you see all the perimeter here, the A's and the C's and the B's. These are all lower complexity modules that you want to minimize the cost. And so 100 megabit Ethernet was previously the lowest speed, now 10 megabit, a lower cost. So we can optimize the overall architecture, optimize the power and signal distribution. So you have less cost, less wires, less weight. If you have less wires and less connectors, it's simpler to assemble, and consequently less components to go wrong, less connections to go wrong. So it's higher reliability. But there's a cost of optimization. You're adding switches and complexity. And one of the goals of 10BASE-T1S is to avoid some of the complexity and the cost of automotive Ethernet by eliminating, not introducing a form of Ethernet low speed that doesn't need switches. So the goals for 10BASE-T1S was to provide an Ethernet and IP-based network, similar cost to replace CAN, but make the network more homogeneous, reduce or eliminate the need for gateway modules. And some of the other features that were added to 10BASE-T1S to add even additional value were POODLE, or power over data lines. And you can think of this as similar to power over Ethernet for consumer and IT devices, but tailored specifically for automotive. So now you have devices, low-cost devices, instead of having power, ground, and then a twisted pair for Ethernet, you only have two wires, so even more of a cost advantage. And then bus and multi-drop architecture. So Ethernet's a switched architecture. It means it's a point-to-point connection between each device and a port on a switch or another device. 10BASE-T1S is a bus architecture, very much like FlexRay and CAN, where all the devices share the same physical media. Some of the background that led to cost reductions on 10BASE-T1S, but lower speeds, you have a lot of trade-offs that move into your favor. So high speed, 100 megabit and above, requires high multi-bit, high speed analog to digital converters, equalization, because it's full duplex, full communication at full bandwidth in both directions. It needs some echo cancellation, so some more silicon complexity, complex clock recovery, and baseline wonder. When you move to 10 megabits from 100 megabits, you can do very simplify how the information is encoded on the wire, going from multi pulse amplitude modulation, where you have different voltages on the network or on the physical, to just comparator. So you use Manchester encoding, which is just looking for edges, and Manchester encoding, self-clocked, self-balanced, and you don't need echo cancellation because it's half duplex. So moving to a bus architecture at a lower speed allows to take significant complexity and cost out of the silicon to implement the network. So the timeline of 10BASE-T1S, in 2018, the idea was proposed to IEEE, and it got approved under the amendment 802.3 CG. 802.3 is the IEEE standard that defines all the different physical layers. So optical, electrical, wireless, they're all 802.3. CG is the amendment specific to 10BASE-T1S. Additionally, there was a technical committee created in the Open Alliance to help with interoperability along the way for 10BASE-T1S, to ensure that if supplier A goes with silicon vendor B and supplier C goes with silicon vendor D, when you plug these modules together, things have a high confidence that they're going to work. You're not going to have problems between silicon vendors or different implementations between tier ones and how they use the hardware. So within 2 years, 802.3 CG was published. And then in 2022, silicon became available and got into the hands of the tool companies and OEMs and tier ones. And something occurred called Plug Fest at Automotive Ethernet Congress. And this is where people from all different levels of development, silicon manufacturers, tool manufacturers, tier ones, OEMs, bring devices together in a room, plug them in, and hope for the best. And if you've never been to one, I mean, they're very entertaining, frustrating, but you learn a lot in working through the problems side by side with everybody else. So over time, these plug fests get more and more refined, and there's less and less problems. But in 2022 was the first plug fest for 10BASE-T1S. In 2023, Intrepid came out with the first commercially available 10BASE-T1S tool after we worked out a lot of problems at the initial plug fest. And with our first tools, we started on basically a tour of the world for training all the customers that are interested in 10BASE-T1S. So in 2023 through 25 and ongoing, we've done classes in every region. We trained over 2,000 engineers worldwide for free, and we continue to do so as the need arises. And we continue to revise our training based on new use cases, things we've learned, and new capabilities of the hardware. So I'm just going to share my learning curve with 10BASE-T1S. So after the Plug Fest and diving into tools, me being a product manager, I needed to come up fast, learn how these tools work, help our customers. So I started reading, how does this work? This isn't so bad, it all makes sense, until first time I plugged everything in and I had no idea how this worked. So I take a step back, do some more reading, talk to some people, and I start to get this. I start to get some confidence, and then I hit a wall and no, I'm not. Then I go, yes, I'm getting it. This is stupid. Well, maybe not stupid. Maybe I'm stupid. And then they come to me and say, hey, you know this as probably as well or better than anybody in our organization. We want you to put together a class and teach this. And at that point, things kind of bottomed out because of the pressure. And then, of course, over time, things came back. And I want to show this kind of inflection point over here because before I started teaching this, it was just cycles of reading and then experimenting to the point that I realized I didn't know what I thought I did, going back to reading, talking to people. So, I had this cycle, and in teaching, it really accelerates your knowledge because you're all the questions. And if you want to really learn something, try and teach it because you really need to teach yourself or get yourself to a level above to really be confident in teaching it. So my goal in teaching and the labs we've done is to hopefully have our customers avoid this cyclical these cycles of gratification and frustration, and then really hit the ground running. The basics of 10BASE-T1S. It was designed, keep in mind, it was designed for minimal microcontroller resources. So these are small modules controlled by low-cost small microcontrollers. So they not only have limited memory, they might have limited number of pins available. So there was special consideration to come up with physical layers or PHYs that support a 4-pin SPI interface as opposed to the traditional 10, 12 or more pin media independent interface. It's 10 megabits. I'll explain the significance of this 4-bit, 5-bit encoding. And it was designed specifically for automotive. It's specified at least 8 nodes on a single twisted pair, wiring similar to CAN, FlexRay, or even 100BASE-T1. And some of the terms you'll hear with the physical layer are mixing segment. So mixing segment is you have 2 end nodes that have termination, and the mixing segment is the twisted pair that connects the 2 end nodes or the 2 terminations. Then you have what are called drop nodes, and these are the nodes that are connected to the mixing segment. And the mixing the distance between a drop node and the mixing segment needs to be 10 centimeters or less. So that if I don't think people realize how short 10 centimeters was until we started wiring this up. It's about not very practical in terms of designing vehicles. So one way to think about meeting this 10 centimeter length is to basically have a daisy chain or in and out connection of the nodes. So you have 10BASE-T1S coming in here, and then maybe going through some board traces and straight out, or possibly even double crimped on the connector. And that minimizes the effective stub to the traces on the board and the connector. One of the defining features of 10BASE-T1S is it uses something called PLCA, physical layer collision avoidance. I'll explain the significance of that in the next few slides. And then the Poodle engineered power delivery over data lines. 10BASE-T1S is a PHY or physical layer implementation. If you're not familiar with the different layers of the OSI model, physical layer, the lowest layer, these are the types of things that it defines or specifies. So if it's a copper, fiber, radio frequencies, the data rate, is it a bus, ring, star? How are the signals or devices synchronized for communication? Is it half duplex, full duplex? The cables and connectors. How's information represented on the wire? Is it different voltages? Is it PWM? Is it Manchester encoding? And then the data encoding. How is the data represented on the wire itself? Is it, you'll see the significance of that as well in the next few layers, but in most high-speed or higher-speed communication networks, especially Ethernet, there's more information on the wire than just the data. You have symbols or communication between the network devices that's needed to maintain the link, but it's not the communication or the data between the devices using the network. 10BASE-T1S uses differential Manchester encoding, so it's a very simple encoding that is basically edge triggered. So you have a carrier or a waveform at a given frequency, and a 1 or a 0 is determined by if there's a clock or a state change between clock edges. So in this case over here, we have two clock edges with no signal change. So this is a 0, 0, 0. Now you'll see between two clock edges, there is a transition. So this would be a 1 and this would be a 0. So this is how the data is encoded, the signals are represented on the wire. Media access, this is another thing that's defined in the physical layer and is very important. If you're familiar with the legacy networks, I'll explain how the media access works for them in contrast to 10BASE-T1S. So LIN and FlexRay they're all bus topology, so all the devices share the same wire. So you need a way for devices not to talk over each other or interrupt or interfere with communication with each other. And the way LIN and FlexRay do it is that they are a scheduled communication. So LIN has a master and a schedule table, and it tells all the devices that when this table tells the devices when they can transmit. FlexRay, very similar. TDMA, time divided multiple access, means that there's a schedule. Time slices within a cycle are reserved for specific information or specific modules. CAN has non-destructive arbitration, so that means everybody can try to communicate at the same time, but during the beginning of the transmission, during the header, there's an arbitration ID, and the devices are able to recognize that there is another device on the network with a higher priority. So when it's recognized that the device no longer has priority, it backs off. So ultimately, there's only one device talking or using the bus. 100 base, 1000 base, multi-gig base T1, the higher speed automotive Ethernet. It is a switched network. So you don't have devices, you only have two devices connected to a median. So you have switches connected to ECUs. Each one of these connections is an independent network with full duplex communication, so there's no opportunity for collisions. What makes 10BASE-T1S unique is the way that it avoids collisions. And it's called PLCA, phi-level collision avoidance. And the way the algorithm works is nodes on a bus are assigned IDs, 0 through 255. And there's something called a transmission cycle. And what that means is nodes transmit in a round robin sequentially by node ID. So node 0 transmits, and node 1, node 2, node 3. And the way the cycle works is it's optimized to ensure that if devices don't have something to transmit, it doesn't waste the bandwidth. In FlexRay, if you have 1 millisecond time slice associated with certain data, but that data is not transmitted, and you have a 10 millisecond cycle, you're wasting 10% of your bandwidth because nothing's transmitted in that window. The PLCA avoids this. The way PLCA works is there's ID zeros designated a coordinator, and it sends out a signal or a symbol on the bus that tells all the devices, okay, here's the start of our communicator transmission cycle. And after the beacon, node 0 has a time slot, and it's eligible to send a packet. Then node 1 has a time slot, node 2, node 3. So they do this in sequence. If node 1 does not have something to transmit, there's a timeout period where the next device identifies this and is able to transmit. As I alluded to earlier, there's 4-bit to 5-bit encoding, and this is necessary in most forms of Ethernet for different reasons. In 10BASE-T1S, you need to transmit data, 16 bits in 16-bit or 2 bytes. But you need a way to represent or communicate information on the wire between the PHYs to manage this PLCA. And those types of symbols are, for example, the beacon. That is something that needs to be sent on the wire, but it's not data. So you need to have more. You need what 5 bits does is it gives you the extra space in the encoding to allow for these symbols. So you have a beacon, which designates the start of a cycle. You have start of stream delimiters, end of stream delimiters, and some error, some error indicators as well. So this is why when you look at the physical layer, like on a scope, you'll see things in 5-bit groupings instead of 4-bit because there can be extra information transmitted. So if you were to look at different scenarios on the bus, this is called an empty cycle. So you'd have a beacon. Each node has called a transmit opportunity. Typically that is 32 bit times. So if node 0 doesn't send anything within 32 bit times, it's node 1's time slot, and then node 2, node 3. So you'd have beacon and then a bunch of empty transmit opportunities and another beacon. In this case, if every other device needed to transmit, you'd have a beacon. Then at the beginning of when a device is going to transmit something, it sends a commit symbol, and that tells the other devices that the node 1 intends to transmit something. And this is one of the special symbols, then transmits the packet, and then there's some end of frame symbol communication as well. Then transmit opportunity for number 2, it doesn't transmit anything for 32 bit times. Cycle node 3 transmits nothing in node 4, and then it goes back to node 0. So, and then if you look at all the nodes transmitting, this gives you a worst case latency. So you know the number of nodes, you know the number of bytes in a maximum frame, and so you have a maximum latency calculated. So it's not strictly deterministic by like FlexRay, but it's more deterministic than CAN. And the reason I say it's not strictly deterministic is this cycle time can stretch and shrink based on the size of the packets and the number of nodes transmitting. And you can see the PLCA configuration is a very simple thing. It's the ID of the node, the ID assigned to the node, the max number of nodes, the transmit opportunity timer, and then burst mode, which I won't have time to get into today, but it's a feature to help manage quality of service on the network. One question is, what happens when there's no coordinator to coordinate it? Jokingly, it's fine, everything's fine. What could possibly go wrong? It's not exactly fine, but fortunately, PLCA uses the exact same signals as what preceded it, the CSMA-CD. It's not very efficient, but it's better than no communication. So if there's no beacon within 13 milliseconds, the devices will fall back into this limp home mode, CMA-CD. And then if a beacon comes back, and the devices go back into PLCA mode. So in summary, PLCA it's a more optimal performance than some of the other means of managing collisions for a shared bus. I didn't mention it earlier, but it solves the babbling idiot problem. So there can be a problem where if a device has a defect in hardware or software, it could just dominate the bus and not let other devices transmit. There's hardware in the hardware. It's prevented from a device transmitting more than it possibly could at 10 megabits in a 1500 byte frame. The round robin scheduling gives fair access to the nodes. What was network engineering is now a very simple configuration, 4 or 5 different parameters you need to configure. So it sounds easy, right? Well, why wasn't it invented until 2018, 2020? One of the constraints was that to make this Ethernet, one of the things that defines Ethernet is it has the same interface to the Mac for everything. So all the signals, they needed to implement PLCA without changing the upper layers of the OSI model. So that was the complexity there. And it wasn't trivial to find a way to take this given signals that were defined 40 or 50 years ago and make them work for a new idea like PLCA. But it was done. And so both mechanisms are supported, CSMA-CD and PLCA on the same interface. So the frequent questions that have arisen over the last 2+ years: why only 8 nodes? One of the biggest criticisms by the people that knew CAN, loved CAN, were comfortable with CAN was CAN can have a lot more nodes than 8. And I think this misunderstanding stems from the fact that when you read a standard, I think people tend to think that everything in the standard is a requirement. And that's not necessarily the case. The intention of this statement was support at least 8 nodes over 25 meters. It's a non-normative, therefore not a requirement. When they made that statement, it was based on typical use cases. They thought it was a good place to start. In reality, the real requirements aren't the number of nodes or the length of the cables and things like that. The real requirements are in the mixing, the impedances, the insertion loss, the return loss of the characteristics of the media, the media dependent interface specification. So at the module or at the PHY, what capacitance, what resistance is there, and then electrical specs on the physical media attachment. That's a subsection of the PHY, so jitter and things like that. So all of these are what really are the requirements. It has nothing to do with 8 nodes. But what this implies is you can definitely have more nodes and more reach, but it's going to be a more challenging problem to solve in terms of cables, connectors, circuit boards, etc. So the first question following that explanation is, all right, if I put more 8 than 8 nodes, what really is the impact? So this is a normalized, some normalized data from a study that some friends at Ford and Ampere put together. 80% of the system capacitance on the bus is from the PHY and then the common mode choke, which connects the PHY. When you have more capacitance, that leads to lower noise immunity and jitter. This is something called an eye diagram. So it shows the rise and fall times of a given signal. The more capacitance you have, the slower the rise time. The slower the rise time, this eye height closes, and this eye height correlates with your signal to noise or noise immunity. Also, as these round, these transitions here become wider, and that correlates with jitter. So the jitter and noise immunity are 2 things that are important to signal quality. So you can see as you add nodes, no surprise, the impedance goes up, and so your eye height goes down. So you can see 8 nodes, things are pretty green, and then things drop off somewhat, not rapidly, pretty evenly. But once you get to 12 nodes, things are really questionable in terms of having a good signal quality. Similar with jitter. The more nodes add more jitter. And the other thing is now you have different nodes at different locations on the network. So one node for a given network, one node might have acceptable jitter, but a node at the far end, in this case, the node at the far end has acceptable jitter, but nodes in the middle do not. So it's a lot of trade-offs, and you're trying to balance the system will work for all the nodes on the network. What about 25 meters? So it defined it as a minimum requirement. The main parameters to consider when going past 8 nodes is restrict the capacitance for each node. So that can be a characteristic of the PHY you choose, the ESD, electrostatic protections, and then your layout. And so Ampere did some studies and came up with some best practices or design rules for the number of nodes in the maximum impedance per node to have the highest probability of acceptable signal quality for each node on the network. Other things that can levers that can be thrown or moved can be the signal to noise margin for meeting EMC requirements, or that PLCA timeout transmit opportunity timer. You can increase that, and that can have positive effects in terms of signal quality and not having dropped packets, but it also wastes bandwidth as a result of that. So that's a trade-off. So if you want more nodes, you have more nodes, more trade-offs to examine, and more engineering effort. The question, how important stub length? Many working with 10BASE-T1S, and myself included, find it much more problematic than CAN or even 100BASE-T1. Max 10 centimeter stub length is not very practical. And so it helps understand what's a stub and what is not a stub. So, for example, in this case, if you have an edge node with termination in it, this can be much, much longer than 10 centimeters because it's actually part of the mixing segment. So this is not a stub. This is a stub. Longer stubs may work. Might work on your bench and might work in a vehicle until they don't work, until you have a problem. So when you have longer stubs, it results in impedance mismatches, which result in deflections and bit errors. You also have problems with transmission line characteristics becoming prevalent. So the simple solution is contain the stub to the ECU. And again, I showed it in an earlier diagram where you have dual pins in an ECU. So you're routing it in one set of pins and out another set. And this minimizes the stub length to basically the connector and the circuit board traces, which should be manageable within 10 centimeters. Question 3, why isn't this working? In other training, one of the most common problems is often the most simplest one in terms of linking or communicating. It's the wiring. And one thing that I think we forgot from back in the CAN days is how important termination is. So almost every single time I sit down with a customer and I see collisions, basically what looks like devices trying to talk over each other. That means PLCA is not working. It could be a PLCA misconfiguration, but almost every single time its termination is not there, or it's not in the proper location. So you could have physical collisions. The other thing is there's different types of termination. In a lot of bench setups, you have just parallel termination. It's one resistor across the twisted pair. In practice, in production, you got something called a split termination. that gives the same impedance of the 100 ohms, but it has a resistor and a cap that effectively filters out noise to ground. So in some cases, adding a split termination can solve problems as well. Why do I have poor SQI? The obvious cause, there is a very strong correlation with SQI and how neat your setup is, how many loops or bends or knots you have in your setup. But also, you need to understand how SQI works on 10BASE-T1S. It's quite different than the other forms of Ethernet. First of all, it depends on data reception. In other base like T and base T1 networks or physical layers, when data is not being transmitted, the PHYs are exchanging symbols, and symbols for just managing the link. They're idle symbols to keep the link active, communication with, and those symbols can be used to calculate signal quality. 10BASE-T1S, if it's not transmitting anything, there's no symbols, there's absolutely nothing on the network or on the physical layer to calculate a signal quality. There's no signal. So you need to be transmitting. The other thing is the topology. Remember, it's a bus, so there can be some context between the SQI. So the default SQI you might be reading could be SQI for an aggregate of all the devices on the network, or it could be an SQI where the device is configured to calculate exactly one device and the SQI associated with it. So it's really understanding how it works and then understanding some of the nuances with the configuration and how SQI can be calculated and reported. So in my experience, it can take a second or two at 10 megabits, on the order of 10 to 15,000 frames, which can take a few seconds before you have an SQI to report. And then another thing that affects is node distribution. And this is something that I only became aware of within last year, again, because of some studies with some colleagues in this area. Node distribution. So it wasn't intuitive to me, but how the physical distribution of how nodes are connected to the bus. So nodes in proximity exhibit something called a stack capacitance, where where they're close together, the capacitance is combined or acts like it's in parallel. And so this can affect the signal integrity similar to system capacitance. So these devices can effectively have a different system capacitance than the other devices. So Ampere and Ford and others have done work to characterize or come up with standards or best practices on how close can nodes be as a function of nodes. So at least with Ampere, less than 5 nodes, they found 30 centimeters was needed to be the minimum distance. When you start adding nodes, that distance increases upwards. When you have 12 nodes, they were finding it needed to be 80 centimeters. At lengths or distances below that, you started to have degradation of performance. How is TC10 different for 10BASE-T1S? If you're not familiar with 10BASE-T1S, it's the Open Alliance standard for automotive Ethernet sleep and wake up for PHYs. So TC10 is a global topology, so it's independent of wake up signals. It's intended so that the PHYs can wake up independent of the microcontrollers that they're connected to, so it can more rapidly bring the network up and bring the car out of sleep. So the PHY can wake up before the microprocessor, actually wake the processor up, and things come up in parallel. The differences in 10BASE-T1S versus other automotive Ethernet stem from the fact it's not point-to-point. It's a bus. So in some ways, it's similar to partial networking can, and that nodes can be selectively put to sleep, but and they can be awakened from a local pin or from the bus. But in 10BASE-T1, or sorry, 100BASE-T1 and the higher speeds, the sleep requests are between the PHYs. In the case of 10BASE-T1S, that's not the case. The application has to put the PHYs to sleep. The other difference is the wake up. So the bus topology is a bus topology. So if you're going to wake one device up, you're going to wake them all up. And so in the multi-port modules, they could be waking up on one 10BASE-T1S in the case of an aggregator, and then you could forward that wake up out other ports or other to other 10BASE-T1S subnets. So one of the problems to solve for 10BASE-T1S was we want PHYs to go to sleep, but we don't want normal communication to wake them up. We only want a wake request to wake them up. So the way they solved this problem was something called a wake-up tone. So it's a transmission that's out of band or much, much slower than the bit rate of the 10BASE-T1S. So the devices can filter out while they're asleep, basically filter out all the higher speed communication, but stay in a mode where they will recognize this wake-up tone, and that will allow them to wake up only on the wake-up tone and not wake up on normal bus communication. Okay, just a time check here. I got started a little bit late, so I got 3 minutes to get through probably 8 or 10 slides, so I'll try and get through them as fast as I can. You're welcome to stay on as long as you're able to follow this, or I think we're recording this and we can post it as well. But so wake up sources for 10BASE-T1S and TC10. You can have remote PHY wake up pulse, or the local sources can the host controller or a wake up pin is connected to a wake up signal from another PHY. So one PHY could wake up another PHY. Once the wake up pulse, it can be forwarded out of the module with multiple ports, and then you have a local wake and a wake forward. You can combine these in a logical OR so that either one can be the wake up. How's time synchronization different on 10BASE-T1S? GPTP. Difference here again, based is not only the shared network, but the shared media, but the fact it's half duplex. It uses the same messages, the same sync and follow up. It has some restrictions in the signaling and the messages that are used. But the primary difference is if you understand GPTP on a point-to-point network, like a switch network, two devices are just transmitting back and forth. And these messages use a multicast address as a destination. So this device is going to send a multicast address. This device is the only one that can receive it because they're on a independent link. But if you have multiple devices all transmitting to the same destination address, there's no way for this the transmitter or the receiver to resolve who's transmitting what. So the way this is resolved is, fortunately, there's additional information in the GPTP header called a requesting port identity. So this is additional addressing information. So this is used in GPTP on 10BASE-T1S to resolve anything between receiver 2 and time transmitter. They look at the requesting port identity as opposed to just knowing which device that they're connected to. So once that is brought into the the state machines now, everything works exactly the same as this if it does on the other forms of networking. 10-base, I'll just go over 10BASE-T1S tools and some of the things that have evolved. Use cases are the same as primarily or fundamentally the same as other automotive Ethernet tools, media conversion, monitoring, gateways, testing for sleep and synchronization, simulation. One of the differences or additions is testing the PLCA compliance and performance. This doesn't exist on the other networks, so this is a new feature, a new requirement for the test tools. And then the desirable features, again, a lot of them are the same, but the differences have to do with PLCA status and symbol decoding. So we've covered the status and symbol decoding. One use case some customers come up with is the ability to send corrupt or invalid PLCA symbols. This is something that it's on our radar, but it's not a trivial amount of effort to implement this. So we're waiting for more demand from customers. We don't want to invent something looking for a problem. We want to invent something or deliver something that already has a problem. So if you know of a requirement or have a requirement to for your tools to do this, please talk to us and we can talk about possible options. One thing that's not apparent to a lot of people when they first start to understand PLCA is that the PLCA symbols are only visible to the PHY. They are not visible to the upper layers. So you're not going to typically see the commit or the start of stream delimiter or all these symbols in a log because they are stripped before they're passed up the stack. But these are very, very helpful in looking at the utilization of the network, the bandwidth utilization by bursts, the latency effects of different communication patterns. So we looked for a way to log these symbols or detect these symbols and make them available for this type of analysis. So what we came up with in our tools is we have 10BASE-T1S coming in front end on the circuit board, and then at that time it's split. The signal goes through the T1S PHY as normal through the MII to the processor, but we split this signal and do some signal conditioning on the Manchester encoding, and then have that go into the processor as well. And the processor is able to decode these PLCA symbols and timestamp them. So now on the computer or in a log, you have the packets, the symbols, they're all timelined, and you have a very clear picture of what's going on the bus. And so this can be helpful to look at in real time and verify that you have proper PLCA behavior. You're getting a beacon every periodically. Nodes are transmitting, and you can debug miscommunications. You can if you have a static, persistent, or periodic fault, you can look at it and try and set triggers and try and capture it based on PLCA symbols. Another use case would be post analysis, and so this is where you want to look at data that you can't really get a grasp of looking in real time. So you take a longer log and then run some scripts on it, and you can extract pretty much any statistic or behavior, look for behavior with these. In a lot of cases, the most frequent things are looked at are latency, size, packet size, bandwidth consumed, empty cycles, or how is the device using all the bandwidth allocated to it or not. So this was very helpful in comprehending how the network works under different loads and different applications running. But this really paid off at Ampere or Renault PLCA compliance. So some of the earlier plug fests, there were some non-compliances or interoperability problems between PHYs. And so Renault did a follow-up, and they brought some PHYs from different tier twos, an oscilloscope, and prior to this, PLC analysis was used mainly for just understanding trade-offs in the number of nodes and configurations and things. But in this case, it was actually used to find an interoperability problem. So what happened was they did an analysis, and looking at the latencies, they just couldn't understand why there was this outlier in this node in terms of latency. So this gave them, this didn't tell them exactly what was happening. It was just a flag to tell them to dig deeper. So then once they had an idea of what was going on, or an idea where to look, then you bring in the next level of debug. In this case, it was an oscilloscope. And then once they were able to start refining of what they were looking for, they were actually able to find a case where a commit symbol of one PHY was interfering with the transmit opportunity of another PHY. So this is something that I don't know if you would ever, it would probably just be this random error that you just never really got to the bottom to because you didn't know where to look. In this case, this capability and tools was able to give a starting point and let the customer, let Renault drill down until they actually found the problem and were able to identify it, and it was ultimately corrected in silicon by one of the vendors. So in summary, 10BASE-T1S went from concept to spec to being featured in prototype designs in 4 years. In the last 3 years, the demand of training has grown rapidly. We've done complimentary training over 2,000 engineers globally. We continue to do it. Not only the demand for training in the new technology, but Ethernet. There's another wave of engineers or subsystems that are just being introduced to Ethernet. So a lot of the engineers responsible for the less complex modules have not been introduced to Ethernet. They stuck with CAN or stuck with LIN. Now, as this Ethernet trickles down to the lower cost modules, now there's a whole different audience that needs to learn Ethernet. And we also provide training just on Ethernet, automotive Ethernet in general. There's been a strong demand for new tools, new features, so the PLCA analysis. There's emerging standards for what's called a remote control protocol, which is means to tunnel other protocols through automotive Ethernet like SPI or I2C, tools for the power poodle, and then security tools, different applications with the number of ports between 1 and 8 T1S ports. And we see the demand for training tools expected to continue as 10BASE-T1S evolves and spreads to other parts of the vehicle. As this continues, we continue to put a high priority on in training. We find it mutually beneficial. I can tell you, as a trainer, I can't tell you how much I know as a result of questions in class that it just never occurred to me. So I went off and found the answers, closed the loop with the customer, and then we're both better for it. So I'm an expert in a lot of things, but I'm not an expert in everything, especially in Ethernet. So I really appreciate the opportunity to train because it builds my expertise. So I'd invite you to contact us about our training schedule. If you don't see something on our schedule or have something kind of a niche or maybe a narrow scope topic, talk to us. We'd be more than happy to discuss with you opportunities on how we might help you out either with tools training or software solutions. So with that, I'm 10 minutes over. I don't think it's too bad given the late start. I don't know if there's any questions. If there are, I'd be more than happy to answer them. If there are not, I really appreciate you taking time to listen to this. And by all means, please contact us with questions, anything 10BASE-T1S or automotive Ethernet or automotive networks in general. We'd love to talk to you and understand your needs and the problems and help you with them. Thank you very much.